Okay.
Continue.
Yeah.
So large files stored in GFS will be huge. Large sequential and small random reads. Workloads primarily consist of two kinds of reads: large streaming reads and small random reads. Sequential writes. The workloads also have many large sequential writes that append data to files. Typical operation sizes are similar to those for reads. Once written, files are seldom modified again. Not optimized for small data. Small, random reads and writes do occur and are supported, but the system is not optimized for such cases. Concurrent access. The level of concurrent access will also be high, with large numbers of concurrent appends being particularly prevalent, often accompanied by concurrent reads. High throughput. GFS should be optimized for high and sustained throughput in reading the data, and this is prioritized over latency. This is not to say that latency is unimportant. Rather, GFS needs to be optimized for high performance reading and appending large volumes of data for the correct operation of the system. Use cases. GFS is a distributed file system built for large distributed data intensive applications like Gmail or YouTube. Originally, it was built to store data generated by Google's large crawling and indexing system. Google's Bigtable uses the distributed Google file system to store log and data files.
So, Srini, your about your point, right? The generic distributed file system or generic distributed storage systems, right? So the reason I wanted to differentiate between these two is like now like we also have databases, right? Databases can also act like a distributed storage system, or like the logs that they talked about, right? We can have a distributed log storage too. These two are like slightly different than the distributed blob storage or like object storage systems. So that's the contrast I actually wanted to build here.
Actually, I don't think so. Underneath the same, because I think this architecture. I think he's more talking about the application level actually. But underneath, right? I mean, I'm pretty much sure the use case for this document should be kind of either Google Docs or kind of any, right. I mean, Google YouTube's, right. I think they will be using same thing, but underneath how they are processing the data and all, maybe they're using the Spark or whatever the pipeline or those engines. But I think it should be one at the end. It should be the same actually.
Yeah, you mean to say like, yeah, definitely, like it's just like object storage. Wherever object storage is being used, like even when you say Google Docs is an object storage use case only, right?
Yeah, that's
Uh,
right. Right now, almost
but
all are
yeah,
object storage. Yeah.
yeah, but the reason like Google Docs and other things are not of particular interest is like I wanted to differentiate is because like Google file system doesn't involve big size files, right? Like GBs or like huge files or like that. So that's why the workload doesn't come that significantly in those processes. Like for example, like particular talking about Google Docs. But let's say if it is about storing YouTube files, like that is like a significant one, right? So that needs to be stored as a object storage, for example. I'm just trying to differentiate between docs versus this thing. Or let's say for example snapshot, for that matter, any service could have a snapshots. So snapshot could be treated as like a big file or like a object storage. Is the uh, primary, it has a primary use case for object storage, right?
No, it can be right, because for, I mean, but block storage or object storage. I mean, so typically like how we organize the data, right? And that is the only difference, right? I mean, either block or object or the file system, I mean, file storage, right? Uh, but distributed storage, they are talking about the block store, I mean, object store. But again, it is not for the small files also. Small files means, I mean, it cannot be a KB file, right? Because any file more than 10 KB or whatever, it has to be split. It has to be split, right? Because it's a multi-part only, almost all uploads are, right?
Um, I would say like that again. That's also a different discussion, because like I have seen like multi-part like algorithms or multi-part protocols where the chunking is defined or customized, or the chunks could be as big as 50 MB. So if as long as it is 50 MB, or let's for example Spring Boot libraries, they generally support up to 100 MB of chunk size. So like that. So multi-part only happens, whereas like most of the like few databases are able to handle those sort of heavy files to like almost up to the MBs versus the KBs. So I will say like that's like multi-part is a different scenario, right?
No,
Whether
what I'm saying is,
we can.
what I'm trying to say is, multi, even in GFS, I mean, the Google file system also, right? We have to do a multi-part because that's or else we can't send the data. Maybe we will read it further.
Yeah,
But how can I send the data from the application layer if I don't do a multi-part, right?
yeah, correct.
Because that's what I'm saying.
Okay, understood, yeah,
But maybe we'll read it maybe a little bit.
yeah, yes.
Yeah, I think this guy, this one, he's talking about from application level, how to design. That's what I mean. If you see, right, it is not the backend or in-depth design. It is like more on the how to create APIs, how you discuss with underneath storage. I think storage system is different for this. I think I don't know whether they covered the actual storage system in this paper.
Like I didn't get you.
You know. So here, right, I think in this paper, right,
Yeah.
it's a more on the application section. Like that means like uh, more like defining APIs, how you get the data from the underneath storage. I think underneath storage, right? I'm not sure whether they are interlinked with HDFS or some other storage. But the GFS, I mean, I was just skimming through. They were talking more in the application layer, high level architecture. This is not the actual storage system architecture.
Okay, makes sense. So okay, I think I understood what you mentioned. Yeah. So basically, storage system will be one of the component, but they haven't discussed that in detail here.
I think so. Yeah, that is what I'm saying. Maybe that is part of some other design. I think.
Yeah.
Yeah.
But actually, the anatomy part that they are talking about, right? Like, so in anatomy part, they have like briefly mentioned these scenarios, but definitely, yeah, there could be a big discussion or detailed discussion about that, the storage components in the anatomy part, like. So like this replication and that they're talking about, right? Data. So basically, usually we have in Hadoop we have data nodes, right? So data node details of data node would be about like the storage system actually.
Yeah. So I mean, I'm not sure to make it very clear for everyone, right? Right now, what they're talking, um, master operations replica. Okay. Not sure actually this one, right? Maybe like we'll go through and we'll read it. I think that's what. But this is for data intensive application. That's what they mention it. Okay. So yeah. So this is not for small use case. This is for really a large use cases. This one is
Exactly.
maybe a smaller use case, but still, right? Data intensive application means like almost all real time jobs and all, right? Part of it, right? So
So, for example, in today's interviews, like whenever there are a machine learning engineer or like ML applications engineer or like that kind of roles, they are using this type of system designs basically, like object storage or like, so just in order to just ensure that like I think I don't know like, but I have seen like few of my friends have been asked this.
So maybe we are not deviating it, but so the one part, right? Any kind of ML, like any kind of normalization or normalizing the data, right? So, I mean, like there are multiple ways, right? How where the data is, right? So S3 or this one is the one use case, or OLAP or OTAP, like or those things will come into picture, right? How the data is underneath the database to run an ML algorithm on top of it, right?
Yeah, so even I had that doubt, Srini. I was briefly also asked similar question. So even OLAP or OLTP, OLAP, any kind of ETL, ELT, all sorts of scenarios, all of them actually have some kind of this Hadoop kind of structures, or like HDFS is the most predominant architecture over there.
Yeah, yeah. That's what I mean. That's underneath storage system. That is, yeah.
Yeah. Okay.
Okay, let's go
Fine.
ahead
We
and
can
try to.
proceed. Yeah.
But I think right now I too have a lot of confusion. Maybe like most of the people are maybe like over the period, maybe we'll come to know what exactly they are doing in this. Right? Yeah.
Yeah, thank you, Ruchir, for reminding about the recording. Please, yeah, uh, people feel free to remind us because, we forget otherwise. Okay, so APIs. GFS does not provide standard POSIX like APIs. Instead, user level APIs are provided. In GFS, files are organized hierarchically in directories and identified by their path names. Oh, that's better. Thank you. GFS supports the usual file system operations. Create is to create a new instance of a file, to delete an instance of a file, open a named file and return a handle, to close a given file specified by a handle, to read data from a specified file and offset, to write data to a specified file and offset. In addition, GFS supports two special operations. Snapshot is an efficient way of creating a copy of the current instance of a file or directory tree. Append operation allows multiple clients to append data to the same file concurrently while guaranteeing atomicity. It is useful for implementing multi-way merge results and producer consumer queues that many clients can simultaneously append to without additional locking. So we talk about the high-level architecture next. We go over a brief overview of the GFS architecture, and we'll talk about chunks, chunk handle, can you go down? Cluster, chunk server, master, and client. A GFS cluster, no, you have to go down. Go up, unless you want to discuss it before we do the next. So we go over create, delete,
So
open, close, read, write.
just one, can you scroll up by 2 3 lines? Yeah, so particularly uh, the first line here, it says does not provide standard POSIX like API. So basically, the general APIs we talk about, that's more like a application layer APIs, user level APIs like that they have talked about, mentioned here. So let's say if you are designing Azure Blob Storage or S3 storage, S3 storage is intended to be used by outside users, like let's say for like developers basically. So in that scenario, we need the user level APIs, or whenever let's say it needs to be exposed universally. But there are applications where, like we talked about, generally YouTube kind of applications, or like certain applications where these HDFS systems needs to sit on top of big size nodes and big basically vertically scaled up servers. And the actual vertically scaled up server is an application server for some other use case. Consider like YouTube. So YouTube might be processing, let's say, particular node might be processing some video file. That video file would be then chunked and stored. In that scenario, the storage layer could be distributed file system, but there the calls will happen locally. So in local calls, these distributed file systems use POSIX APIs, much similar to like what we have like RPC, right? Server to server communication. Here the POSIX APIs actually mimic the same RPC kind of framework. So like for any application, it will feel like it's making a like making a system call, like as in a database layer call or driver call or like that. But actually the POSIX layer, POSIX API layer will take care of basically routing that call to this distributed file system. So whenever it needs to proxy the local storage kind of scenarios, they use the POSIX API. So just keep that in mind. Like it is just a different way of having the APIs for the for making this as a local storage, like, or making it feel like a local storage to any application server or application system. Versus the user level, where we will be exposing it like the APIs which we discuss on Saturday Sunday, those were like user level kind of APIs.
So, I mean, so the basic, the POSIX API, right? It's tightly coupled with only the operating system. If you take Unix machine, you can initiate it from there only. You can't do it from any application layer or from uh, from kind of a third party client or something. I mean, you can't do it, right? So it's a glued with the API, and then it talks with their API operating system, user space, and then kernel space, like how interacted. But the what we are talking is that these are REST APIs, right? REST APIs is you can communicate from outside of the system, right?
Yeah, correct. So these you talked about this like local like low level or system calls, right? Like that, right? Operating system level. So currently there are basically there are certain libraries which actually integrates with those system level calls, and it can actually make it remote calls too.
Correct.
So this POSIX API comes in context with that. Basically, those libraries, the APIs we will be designing will be the POSIX API. But then at the same time, any such library will come as a proxy, and that library will take care of whether to pass that call to local operating system, or pass or convert that call into a remote call to a different chunk server, or basically different file chunk or different remote server. So for example, there is this library called as Fuse. So Fuse is one of the libraries currently being used, which actually does the same thing.
Sure.
I will probably share some link related to that, Shini, in group later.
Actually, in my understanding, there will be kind of, I mean, like, I mean, two or three types of APIs that we usually go with. One is a web API, right? I mean, those what uses the HTTP protocol to transfer data. One is whatever your local API that you're talking about, right? That is tightly glued with the operating system. And the next one is the RPCs, the remote procedure calls, communication between the server to server, right? Um, so here they're talking about they don't go with local APIs or the OS, I mean, POSIX API. Instead of it is everything is kind of web API, right? That's what we can interpret that way, right?
Correct. Correct. Yeah.
Yeah.
Yeah, so maybe, yeah, for timing we can keep that discussion out, sideways. But yeah, I think one article I wanted to share, I will maybe share it later once we cover this, where like for the latest kind of systems, they actually use the POSIX API just to, like, we have a data for the database layer, we have database drivers, and then that call is like calling to the database driver, and then the database gateways will take care of those things, right? But there are other architectures, parallel architectures, where just a normal system call, or the operating system call is intercepted, and then it's made as a remote call to, like, for distributed file systems. So I was just trying to highlight that, but that's actually niche use cases. Yeah, but we'll share that about that later, so that we don't deviate right now.
Sure. So, Annie, so you're reading, right? A little bit.
Yeah.
I think, can you scroll a little up? I think we're doing. So, in this, I mean, in this architecture, I mean, in this paper, they're talking about defining couple of APIs. How do you create and how do you delete, open? Open is for what? Open the file, okay. Close is for what? Closing the file, okay. And read and write. Read and write is file, okay. So, they're talking about six APIs. Um, and the operations they will be doing append. One is append only. That means like any, I mean, like kind of a Google Drive, Google Doc, right? Append and snapshot. Copy of the instance of the file. Okay, so we'll create a snapshot. Okay, fine. Yeah. So I think we'll be covering how those APIs will be met in this architecture. Okay, go ahead. Go ahead.
GFS cluster consists of a single master and multiple chunk servers and is accessed by multiple clients. As files stored in GFS tend to be very large, GFS breaks files into multiple fixed size chunks, where each chunk is 64 megabytes in size. Each chunk is identified by an immutable and globally unique 64-bit ID number called chunk handle. This allows for 2 to the 64 unique chunks. If each chunk is 64 megabytes, total storage space would be more than 10 to the 9 exabytes. As files are split into chunks, therefore, the job of GFS is to provide a mapping from files to chunks, and then to support standard operations on files, mapping down to operations on individual chunks.
So here basically they are just defining what's the smallest part of any big file. Let's say we have a 10 GB file. That 10 GB file, to store a 10 GB file, it will often be, let's consider if it's a if it's a 1 GB file. So 1 GB file can be chunked into some 20 pieces. Each of them could be somewhere around 64 MB, and that 1 GB file will be stored as 10 pieces of 64 MB size. So that each chunk needs to be basically, like, all the metadata related to each chunks needs to be stored, like the file name, the chunk IDs, and there should be a mapping between chunk IDs, and then the locations of the chunk IDs where they are stored, and then all sorts of fault tolerance scenarios in that. So where they are, like, here they are talking about the mapping. So that will be about how one single file is broken into 10 files, and which are those 10 files and where are they stored. So we saw something similar in like in the metadata services, right? Like in like when we were talking about Cassandra and other stuff. So basically this is a common theme whenever we have like multiple chunks or multiple partitions, it will often involve these mapping. So that is an additional metadata overhead.
So, so adding to that point, right? Anybody like who has like were confused for me, this is no way different than any other storage system. Okay, so that too, this is like chunking. It's in the storage level. It is not in the application level. If I assume, because you can't send the 64 MB from one connection. I mean, one transfer. I think this is from the underneath system. Okay, and the backend system. This is right. Because if I want to upload the 1 GB, right, I can't send the 1 GB divided by 64 MB, and then I can't send it from 64 MB from my client. I don't think so, right? You're getting my point, right, Sagar? What I'm saying?
Yeah, yeah, yeah.
Yeah. So don't get confused. I think this is like what they're talking about is uh, just with respect to the storage subsystem. This is.
So how did we derive this 10 raised to 9 exabytes thing?
Sorry, what's
Am
your
I,
question? Can you
yeah, yeah. So I'm referring to the space. It mentions 10 raised to 9 exabytes. So if we go with 2 raised to 64 unique chunks and each chunk is 64 MB, how that calculation is going to 10 raised to 9
so
exabytes?
so actually that's they are just talking about like if we use a system of basically an ID which is of length 64 bit. If we use 64-bit ID, then our system will have unique IDs up to the size of 10 to the power 9 hexabyte. So let's say if it's just one byte, then it will be 0 and 1, right? Or let's say one byte, one bit information would be just 0 and 1. So it will just have two values, right? So these two values, so basically we would be just able to have two chunks that could be referred or uniquely identified by just one bit information. If it's two bit information, it could be four, or just like that, right? So how many unique chunks we can